Good morning, dear students, and welcome to Vista's Learning and online educational platform. My name is Denzil, your physics tutor for class 11. Let's get started with today's session. Today, we will be discussing more about vectors. This is actually a bridge course, and this would be a session 2 based on the topic vectors. Earlier in session 1, we discussed the type of physical quantity vector, a definition for vector, how to represent a vector, and how to identify the magnitude and direction of a given vector. In this session, we shall pay more importance to operations on vectors. Operations such as addition, subtraction, and multiplication. Division of vector is not possible. Why it is not possible, we will soon see. But before we start with the operation, a quick recap from the earlier section, which is to determine the magnitude and the direction of a vector. The method of determining the magnitude and direction of vector in this following case is by a graphical method. So for that, I have two axes, namely the x-axis and y-axis, which are mutually perpendicular to each other. So this horizontal, choose an ink. This horizontal line, I call it x-axis, and the vertical line, I call it y-axis. Now, to locate an object in this plane, which is of an x-axis and y-axis reference, it is given by set of points. So, if I highlight or mark a point in this particular plane, we say that the object is located in this position. And how do we identify the position? By the respective coordinates as x, y. Now, any vector that is drawn from the origin to this position. So, I have my origin located here, and a vector which is drawn from the origin to this position here. So here we notice that this is a vector, let's call it by a letter R. This is a vector, and this vector is called a position vector. This was also discussed in the previous section as different types of vectors. And one of the type is a position vector. Now, how do we identify the magnitude and direction of this position vector? Now, for that, we first consider the projection along the x-axis. So, this would give me the length along the y-axis. This is already the length along the x-axis. Now that you create a right angle triangle, okay, you have a right angle triangle, you have two different components, namely the y component and the x component of a vector. So you have the y component and the x component. So let me highlight that as the y component, whose position here is given, and the x component. Using Pythagoras theorem, we can state that r vector square equals to x square plus y square. So the theorem clearly states that the square of the hypotenuse is equals to the sum of the square of the individual sides. So, to identify the magnitude of a vector, which is r vector, is a square root of x square plus y square. So, this is how you determine for a given plot and a given vector what will be its respective magnitude. So for a vector, is it enough to just show the magnitude? No. Vector relies on two things. One is a magnitude, which can be determined now, and also a direction. So which direction is this vector acting along? Now the direction, usually in the case of a graphical method, is given by an angle with respect to the x-axis. So let's call this angle theta. Now that you have to determine the direction of r vector, right? So which means you have to find the value for theta. You take a trigonometry ratio tan theta, which is defined by opposite by the adjacent side, or height divided by the base. So opposite side is y and the base side is x. So theta equals to tan inverse of y by x. Okay, so I hope you remember this, determining the magnitude and the direction of a given vector. A quick recap. So now we move into operations. Our main objective for today is to deal with the operations on a vector. One of the operations of a vector was discussed in the previous class, which is addition of a vector, where I explained you that addition takes place in two different manners. One is by using the triangle law of addition, and the other is by using parallelogram law of addition. In case of a triangle law of addition, one vector is connected to another vector in such a way that the tail of the second vector coincides with the head of the first vector. Let's call these two vectors as A vector and B vector. To identify the final vector, and why do we need to find the final vector? Because you have two different vector components that are being added. And when you add two different components, you get a result. So this vector, which is a result, is called a resultant vector, which is represented by coinciding with the tail of the first vector and the head of the second vector. So this can be written where C vector equals to A vector plus B vector. So for now, all I'm dealing with is a graphical representation of a vector. There is also analytical representation of vector. We shall look at it later, but first let us focus on graphical representation to get a clear picture as to how these vectors are represented. C vector equals to A vector plus B vector, and this C vector is what is called as a resultant vector or a final vector. You can also call it final vector. So this is the case of an addition of two vectors, A vector, B vector, by a law which is triangle method. There is also another law, the other method of adding two vectors by parallelogram law of addition. Now here's how you add the two vectors. First of all, let's represent the two vectors. One vector acting along this direction, let's call it A vector. The other vector is drawn such a way that the tail of that vector coincides with the tail of the first vector. Well, it is not the same, though it can be made into the same components, but then the diagram is little different. Here is a triangle of addition, and here you have two vectors where the tail of the two vectors are coinciding. Now, how will you identify the resultant vector or the final vector? For this, we construct a parallelogram. So, parallelogram is constructed where the two opposite sides must have equal length. Okay, so I'm going to construct with a dotted line of an equal length. See, this you could say is a projection of a vector. This line is a projection of a vector. Similarly, you can also create a projection of b vector. I hope it is visible, or let me draw it by a different color. Okay, that's the projection of a vector and projection of b vector. So the two meet at a point. Okay, the two meet at a point here. The projection, they meet at a point. So resultant vector is drawn such a way that it starts from the tail of the two coinciding vectors to the point where the two projections meet. So this will be your resultant vector, where C vector equals to A vector plus B vector. So this rule is what is called as a parallelogram law of addition. And certainly this resultant vector has an angle or an inclination to it with respect to A. Okay. Now, subtraction. When do we say that the two vectors are subtracted? Now, first of all, let us discuss from the previous case, let us discuss few properties of this addition of vectors. Few properties like, if I add C vector equals to A vector plus B vector, will it be the same when I add B vector plus A vector? So some of the properties you must have discussed in mathematics, the commutative property, associative property, or distributive property, and so on, right? So let us check the commutative property of this vector addition. Is it commutative? Now, when you add two vectors, that is A vector plus B vector, the result can also be implied that B vector and A vector will give you the same as the previous. So this is equivalent to C vector. Therefore, under addition, two vectors are commutative. All right, they are commutative. Now let's take a look at subtraction of two vectors. When I subtract two vectors, what is the result that I obtain? Let's consider one vector acting along this direction. Let's call it A vector. Another vector now which is acting along downward direction, B vector. One vector acting towards the right hand side is a positive A vector. Another vector which is acting downwards, now we can assign or give a sign to this particular vector. Remember, when you walk forward, you give positive sign. When you walk backward, you give negative sign. When you move towards the right, you give positive sign. When you move towards the left, you give negative sign. When you move up, you represent it with a positive sign, and when you move down, you represent it with a negative sign. Therefore, this B vector, since it's pointing downwards, it will be negative. All right, it will be negative. Now, how do we find the resultant vector, the final vector? Since we have two vectors, an operation that is conducted on them, now what will be the final vector? Where will it be located? Since the head of one vector is connected to the tail of the other vector, use triangle law of addition. Let me choose a different color. I'll choose a different color. Which color shall I choose? Okay, call this C vector. Now the component C vector will be equals to A vector plus of minus B vector. So C vector equals to A vector minus B vector. So this is how you solve the following. So graphical representation of subtraction of two vectors. The same thing can be discussed under parallelogram rule. So one vector which is acting along this direction, let's call it A vector. Another vector which is acting along the downward direction, call it B vector. But as we know, this B vector should be negative. Create the projection, draw the projection of your A vector and the B vector. They both coincide at a point and you construct the resultant vector. And this resultant vector C vector will also be equals to A vector minus B vector. Now let us discuss its property. A vector minus B vector is not the same as B vector minus A vector. It is not the same. Rather, you have to change it by a sign where you get minus B vector minus A vector. So this will give you, so it is not commutative. So we say, therefore, subtraction is not commutative for two vectors. Okay, so it is not commutative. Okay, now that we know how to add two vectors and subtract two vectors, we come to the next concept in understanding position vector and displacement vectors. Position vector, you're quite familiar, where it defines or determines the position of the object. A vector that defines the position of the object. The length of that vector gives you the magnitude, and also the direction is given by the angle. So now that we know a position, can we identify a displacement, or what is truly a displacement? We will have a look at that. For that, I take two reference axes, namely the x-axis and the y-axis. The other ways that you can call this x-axis and y-axis is abscissa and ordinate. So you have your x-axis and y-axis, origin, which is located here. Suppose an object starts at a position located here, let's call it x1 comma y1. Okay, starts from this point and displaces. That displacement I will represent using this, and reaches a new position which is x2 comma y2. An object starts from x1 comma y1 displaces to a new position x2 comma y2. Identify the displacement between these 2 points using vectors. Now when I said displacement between 2 points, I know you're very smart enough to use the distance formula for these 2 points and you tell me what is the answer. That is okay. You would find by distance formula, which gives you the exact same thing you need, which is the magnitude of or the value for a displacement. But then it does not give you a complete set of information. What about the direction? So for that, let us first represent these 2 points using position vectors. So I have my one position vector represented to this point x1 comma y1. This position vector, let's call it r1 vector. R1 vector represents the position vector. Similarly, I will construct the position vector for x2 and y2. Do my best. Yes, nice one. Let's call this R2 vector. Now that I have two position vector, one which represents the initial position, two which represents the final position, now let us calculate the displacement between these 2 points. A vector which represents the displacement between these 2 points is what is called as a displacement vector. So let us see let us draw that here, the displacement vector. A vector, let me repeat that again, a vector which represents the displacement, a vector which denotes the displacement of an object. Okay, so the displacement is in this given direction. I hope that's visible. The displacement is in this given direction along x1 y1 to x2 y2. So connecting these two dots. I hope that's visible. If not, I'll have to pick another color. I'll pick another color nevertheless. If this is not visible, I'll just pick another color. All right. Yeah, that should be good. So this vector is what is called as a displacement vector, given by delta r vector. How do you find delta r vector? Delta r vector, which is equals to r2 vector minus r1 vector. Make note of this. Displacement vector, which is equals to the difference between the two position vectors. Okay, make note of this. So this is how we differentiate a position vector and a displacement vector. Now moving on to the next, which is next operation where we deal with multiplication of vectors. Under multiplication of vectors, there are two different methods we can multiply a given vector, two given vectors. One is by using what is called as a dot product. The other method is by what is known as the cross product. So we shall discuss this both now in this session. So let's get started with the dot product of two vectors. In case of dot product of two vectors, the two vectors A vector and B vector are multiplied to give a scalar quantity. I'll put as QTY. A vector and B vector are multiplied to give a scalar quantity. Dot product also has another name called scalar product. Let's have a look at it by an example. Using analytical method where we defined a vector using base vectors such as I cap and j cap. Similarly, a vector, I will represent it with, let's say, a1 I cap plus a2 j cap. Similarly, b vector, okay, I have b1 I cap and b2 j cap, where I cap and j cap are what are called as base vectors or unit vectors. Now, using the dot product means a vector dot b vector, a vector dot b vector. You see that I put a dot in between the two. So this denotes the multiplication of two vectors is by dot product. So I'll write the terms. A vector has a1 I cap plus a2 j cap dot b vector has components which is b1 I cap plus b2 j cap. Now, using the rule of multiplication, which is by distributive law, a1 b1, so we'll write a1 b1 I cap dot I cap. Similarly, a1 b2 I cap dot j cap. This seems a bit unusual. That's because a1 b1 I have not put a dot in between. I've only put a dot in between I cap dot I cap dot j cap, isn't it? Why is that there is no dot in between a1 and b1 or a1 and b2? That's because a1 and b1 are scalars. They are not vectors. You use dot products on a vector. I cap and I cap are unit vectors. Therefore, you have a dot that is introduced. Now, similarly, we work for the other, which is a2. So, go ahead, write with me a2 j cap, a2 b1 j cap dot I cap plus a2 b2 j cap dot j cap. Now, the rule about the dot product. Okay, here is a rule about the dot product. I cap dot I cap is equivalent to saying j cap dot j cap, where the result is always equals to 1. Okay, on the other hand, I cap dot j cap, which is equivalent to saying j cap dot I cap, will result to 0. Now, why is it equals to 1? Why is it equals to 0? I will soon show you that why it is equals to 1, why is equals to 0. But first, let us substitute it here. So, I cap dot I cap, change the color. I cap dot I cap, this becomes equals to 1, this becomes equals to 0, this becomes equals to 0, and this becomes equals to 1. So, you get the final answer, which is a1 b1 plus a2 b2. This is how you identify the dot product of two vectors. Now, explaining why is it equals to 1 and why is it equals to 0. Now, that is because Dot product of these two vectors can also be written as A vector dot B vector, which is equals to, it's like a formula. Okay, so I'm writing the formula: magnitude of A vector times the magnitude of B vector cos theta. Now, when theta, okay, when theta when theta equals to 90 degree, so here we take conditions. When theta equals to 90 degree, then cos theta is equals to 0. Similarly, when theta equals to 0, cos theta equals to 1. I cap and j cap are unit vectors of x-axis and y-axis respectively. So, change the color. So, let's say you have I cap and j cap. These are unit vectors along the x-axis and the y-axis. Since they produce an angle of 90 degrees, and as we know cos theta when theta is 90 is 0. Oh, yeah, that's fine. I should have written cos 90, but it should be all right because I've defined that theta is 90. Okay. So the entire thing will be 0 when it is mutually perpendicular. When theta is equals to 0 degree, in the case where you noticed I cap dot I cap, the angle between the two is 0 degree, therefore cos theta is equals to 1, and that is why we defined as 1. And since A and B were unit vectors, so we wrote it as 1. But make note of this particular formula where A vector dot B vector equals to magnitude of A vector, magnitude of B vector, cos theta. We will see more example based on this. Okay, nothing to worry about. We will see more example based on this, which is on dot product. But write down the formula as well as the given analytical method where you have the condition that I cap dot I cap, j cap dot j cap is 1, and I cap dot j cap dot I cap equals to 0. Okay. Now, moving on to the next type, which is called a cross product of two vectors. This cross product of two vectors are usually defined with A cross B. So, you put a cross between the two. So, this implies that the two given vectors are operated by a method that is called as a cross product. For a cross product of two vectors, usually when these two vectors are multiplied by this method, it gives rise to a new vector. Let me repeat that again. Cross product of two vectors gives rise to a new vector. This new vector will be perpendicular to the initial two vectors. Interesting, isn't it? So if I have one vector which is pointing along this direction, the other vector which is pointing along this direction, let's call it A vector and B vector. Third vector, by operating on cross product, a third vector is identified where it is perpendicular, that is coming out of the board, perpendicular to these two vectors. A vector that seems to be coming out of the board. More examples, we shall discuss them, but first, how to work with this vector. Okay, example we will discuss, but first listen to the instructions and then we can work with examples. Let's say for A vector, which is equals to A1 I cap plus A2 j cap, and B vector, which is equals to B1 I cap plus B2 j cap. cross product would imply, here's the rule, by using determinants of a given matrix I, J. You have to also add K because you have two components. Okay, I, J, and we add one more component K. Why do we need the third component? Remember, I told you that this vector will be such a manner, when you multiply the two vector, there will be a vector that will be pointing out of the board. And that is why we define it by a third vector, unit vector K. So I cap, J cap, K cap represents the unit vectors. Now we make note of these vectors, A1, A2. Do we have K vector given? No. So put 0. Next, B1, B2. Do we have third vector given? No. So we put it 0. But what if it is given, sir? What do you do in that case? Well, not to worry. All you have to do is just represent it by this B3 K cap. Then here you get A3 and B3. You see? Next is to find the determinant. Determinant of this matrix. How do we find the determinant? You might have learned in your mathematics by now. In the chapter matrices, where you take the first term, first element, I cap, eliminate the middle elements and multiply, cross multiply the terms such as A1, B3 and B3, A3. Or you can write it as determinant of A1, A3, B1, B3. Just to simplify things, this is how you can write the determinant of A vector cross B vector. Then minus J. Next, since you're considering J, eliminate this part. You don't require this now, right? So you eliminate this part and then you multiply the respective elements, cross multiply them, or you write it under a determinant on a 2 cross 2 matrix. So go ahead and mention the following, which is A2, A3, B2 and B3 plus. Now for the final component, which is K, I do not have the space. So here's what I'm going to do. I will rewrite them once again on this side since there is no enough space here. So erase this part. Erase this part here. Too much of mathematics? I know it is. Okay. I understand that there is too much of mathematics, but until you get to a level where you turn mathematics into an art form, you will be following instruction until then. So only the instructions will be given how to solve a problem and how to answer questions, but then the true creativity comes when you have completed, when you have digested all those instructions, and then you have started working on something that is way beyond the imagination, or something that you imagine, you put them in a mathematical format. So until then, yes, you have to listen to the instructions given by your teacher. So in this case, I'm going to write this one more time here, determinant of A cross B. So determinant of A cross B, which, why am I writing all right, which is equals to I cap, and then you have the components, the elements such as A1, A3, B1, B3, and minus J, A2, B3, B2, B3, and then plus K cap, which is A1, A2, B1, B2. And by identifying the determinants of this individual quantity gives you the final vector in which direction it is pointing at. A simple way to represent this by a formula is A cross B vector, which is equals to magnitude of A, magnitude of B, sine theta n cap. So earlier in dot product we noticed cos theta, but here we have sine theta and also n cap. This n cap is what is termed as a unit vector pointing along the third dimension. So these type of cross product are also called vector product, because when you multiply two vector, the result what you get is also a vector. When in the earlier case, when you multiply two vectors for a dot product, you get a scalar quantity, but in this case you get a vector quantity. So this is how you multiply two different vectors, a dot product and a cross product. We'll pick some examples in the next session and discuss more about solving under the dot product and cross product. So that is all I have for today. Do visit us at www.we-learning.in to get more details about the class. I will see you all in the next session. Until then, everyone, take care and have a nice day. Bye-bye.